would like to thank the organizer for the opportunity to make my speech here. And the theme of my talk is two-dimensional hypergeometric series providing solution to the algebraic function of two variables. And first I should say some words about motivation for my talk. And in theory of hypergeometrical function, there is one question to study a singular set for this function. And it turns out that this equation is closely related to the same equation for the algebraic functions. And we study the general algebraic equation of degree n with complex coefficients, and by means of the implicit function theorem, the solutions of these equations can be considered as algebraic function of coefficients. Birkeland in 1927 found that the algebraic equation may be always considered, may be always reduced to the equation of the following type with any two fixed coefficients. And moreover, he obtained the representation of the solution as a hypergeometrical series. And the series you may see here. Gamma is a classical gamma function. Epsilon is a prime to q mu p is root of unity, and beta q and beta p are all vectors with integer coordinates. And after that, Kaprov found that the singularity set for the hypergeometrical series is defined by algebraic equation for corresponding algebraic equation for this series. And so thereby, because algebraic equations set or singularity set for the algebraic equation is totally defined by its discriminant, we should investigate this discriminant to say something about the set of singularities of hypergeometrical series or its domains of convergence. And as for domain of convergence, there were some attempts to describe it. And first I should start from the Horn result. He obtained it in 1885. He described the domains of convergence for a hypergeometrical series of multiplicity 2 and 3. By hypergeometrical series, he meant the power series for which yields all ratios of subsequent coefficients are rational functions. For example, we have a series H, looks like S, where S is a vector with coordinates from natural numbers, and by definition, the ratios rational function of S, where EG is a vector which is J's component is unity and other zeros. His description is based on the computation of domains for diagonal series using the Novosibirsk principle and taking intersection of all these domains. And finally, he obtained some kind of condition for the points. If points belongs to the certain set, the series converges at this point. And okay, the next result was obtained by Cherepanskiy in 2004. they obtained combinatorial description of the domains convergence for the series in terms of reciprocal positions these domains with connected component of the complement for the amoeba of the discriminant set. By amoeba we mean the image of algebraic set under the logarithmic projection. The picture of amoeba I show later. And now to illustrate, to explain the result, we need some facts about the complement of amoeba. The complement amoeba consists of finite number of connected components which are open and convex. And for the amoeba of the discriminant set and the corresponding Newton polytope, there are following correspondence between components of amoeba, vertices of Newton polytope, and subdivisions of segment ON. By subdivisions of segments, we mean the divisions by integer points from this segment. Divisions of this segment. And we have the following theorem. The domain of convergence for the series, which I showed before, is a Reinhardt complete domain such that corresponding domain under the log projection of domain of convergence contains each of connected components of the complement for the amoeba, for which subdivision tau contains the interval and E and Q. Moreover, the domain the Q doesn't intersect any other connected component of the complement of the amoeba. So we have the correspondence between domain of convergence and the complement of amoeba. And to illustrate this theorem, I show the example. There we have the equation of third degree. It is a reduced equation. We have two fixed coefficients. And here we go. Here we get the amoeba of the discriminant set for this equation. There you can see the complement of this amoeba and corresponding subdivisions. For example, this subdivisions is the divisions by integer point 2. And now we have because we have 2 example for this and 3. And by theorem, the component with corresponding subdivisions which contain the segments O3, because we have point Q is point O3. This is that component, and it is the logarithmical projection of the domain of convergence for the series, which represents the solutions for this equation. And now we have the theorem which give us combinatorial description. We have the condition by Horn, and there is the question: can we describe the domain of convergence by functional inequalities? Example of the explicit way. I mean, and in general case, the problem is quite difficult. For now we haven't got any methods, but for the case of two-dimensional, I mean that after reducing the equation has two variables, we may obtain some results. Here we have the trinomial equation, which has 4 terms, and after reducing, the reduced equation leads us to investigation of two-dimensional power series. Let's see the reducing equation trinomial. It is similar to the general case. We fixed any two pair of coefficients, and the series for the solutions to trinomial equations, it has the following form. It's similar to the general case, and the discriminant of the reduced equations plays a main role in description of the domain of convergence, because the singularity set of the algebraic equation is, how I said, defined by its discriminant. And now we have the results for theorem for any pair P and Q, the domain of convergence, dpq for series which represents the solution of reduced trinomial equation is defined either by one inequalities of that type and or by two inequalities of the following type. So we have their describing of domain of convergence by inequalities, functional inequalities, which depends on the discriminant of the algebraic equation. And now we have a couple of examples that I had the amoeba of discriminant the equation with pair O3, which I showed before, and their domain of convergence, which defines by one inequalities, or depends on discriminant. And other examples is the amoeba, the discriminant for the equation with pair 1, 2. And like that, and there have description of the domain of convergence. Then you may see there's 6 cases. It is because the form of domain of convergence depends on parity L, M, N. So
Благодарим докладчика, да. Интересные факты. Please, comments, questions? Ну, давайте еще раз поблагодарим. У нас еще 5 минут.